How does it happen? What does it all mean?
Let's find the answer.
How does it happen?
Let's find the answer.
Day 229 of my science quest, trying to make sense of it all, and wondering how a potato ends up looking like a potato. Well, the truth is, there's a universe of forces at work above and beneath the surface of things that shape our world. Think of something even as basic as a burger. Were it not for the balance of invisible forces, you couldn't stack a bun, a burger, lettuce, or tomato, put it on a plate with a pickle, set the whole thing down on a table, and ultimately eat it. Without forces, the burger would just collapse into a mush. Forces explain why you can sit in a chair and not just bounce off of it like a trampoline, or sink into it like it was water. And forces explain why this burger doesn't just float off into outer space. My science quest today is into the world of forces. You may never look at the world quite the same way again.
Let's find the answer.
The science behind forces is profoundly mysterious on the one hand and extremely simple on the other. The first thing to understand about forces is that a force is a push or a pull on an object, causing a change in its motion. A force is always a push or a pull. These two Jeeps are going to have a tug of war. When the two trucks pull against each other with equal force, their wheels spin, but they don't go anywhere. They are balanced. If one pulls stronger than the other, there's a change. The weaker truck loses ground and the balance is destroyed. Just watch the whole thing again and think. 1, all forces are either a push or a pull. And 2, all forces are either balanced or a stronger force creates a change or imbalance. You can picture the same rules for pushing if you imagine two football squads pushing against each other. As long as they push with equal force, the forces are balanced. This push and pull idea of forces is the foundation of the shape of everything in the universe, like this house of cards. It can only stand when the forces acting on it are in balance. Each card must push on the other with equal force, like the Jeeps or the football players. But if an imbalance is created, the shape will change until the forces are balanced again. So I had already learned some basic points about forces. They are always a push, like the football players, or a pull, like the Jeeps. And they are always either balanced or unbalanced. Another way to think of this balance of forces is to think about what happens when forces are disrupted. This chair is made of wood. It has a shape because the forces holding it together are balanced. If you sit on it, those forces are strong enough so that it stays a chair. But run the chair through a wood chipper, disrupting the balance in a big way, and you don't have a chair anymore. You have wood chips. The forces in our life are all around us. When a potter throws clay on a potter's wheel, she is using forces to do it. The fingers of the potter are touching the clay, dragging on it, using friction to smooth it. Friction is a force of resistance or opposition between two objects. Anytime two things touch, there is friction. You can imagine that just about everything you do day to day involves forces. When you pet a dog, stroking it, you are applying force. Scrubbing a floor or washing a car, you may say you are applying elbow grease to get the job done, but it's really force. In baseball, force is applied when the ball is pitched, and of course when the bat meets the ball. Using forces allows us to work, play, and sometimes create some pretty cool stuff. You may have heard of people trying to bend spoons with their minds. Okay, so that's not how forces really work. Gravity, however, is a force we see around us every minute of the day. It's why things fall, and why we stay on the earth and not float away. This man I videoed talking by his car, both he and his cell phone would drift into space if it weren't for gravity. These plastic cups sit still because the force of gravity is balanced against the force of the counter. But once the balance is upset, gravity is right there, pulling them down to the floor. Electromagnetism is the push or pull force caused by electricity and magnetic fields, and it's what makes TV and radio possible. You, me, and everything around us is held together by electromagnetic force. It's the force that keeps you from sinking into the floor when you walk. In fact, any kind of force you can notice in the world around you that isn't gravity is electromagnetism. If you've ever played with magnets, you know they can attach to things by invisible power. That's electromagnetism too. These forces, electricity and magnetism, are both related to the basic structure of the atom itself. This is where we get into the most powerful force known, nuclear force. I found this basic graphic of an atom from a book about a Danish physicist, Niels Bohr. It's a simplified way to see that an atom has a nucleus holding positive charged protons and neutral neutrons, orbited by negatively charged electrons. The forces of attraction, pulling, and repulsion, pushing, within atoms and molecules is the basis for everything we know as our physical world. Researching for this science quest on forces, I was surprised to learn just how powerful nuclear forces can be. A science teacher told me this little example. Remember the atom structure? Well, imagine that these two pennies are both electrons, each with a negative charge. It would take a force equal to the weight of 40 billion mid-sized cars to push them together. The forces within the atoms are some of the most powerful we know. In much the same way that a potter shapes a bowl using the force of friction, nuclear forces shape our entire world. Everything we see, hear, touch is really the result of gazillions of forces, pushing and pulling, balanced and unbalanced. Now I had learned about the key forces that affect us every day. Friction, the force that opposes motion when two objects touch. Gravity, the force that pulls everything down toward the earth. Electromagnetism, the force caused by electrical and magnetic fields. And nuclear force, the most powerful force known. It's the incredible force of attraction and repulsion between the tiny particles inside atoms. Sir Isaac Newton, an English scientist in the 16 and 1700s, studied forces. Legend says it was an apple dropping on his head in an orchard that led him to develop the theory of gravity in 1687. We also owe our present understanding of forces and motion to his three famous laws of motion. In looking for the perfect way to help visualize Newton's laws of motion, I was lucky enough to be invited to spend a day with a serious golf pro. Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion, unless acted upon by an outside force. That means this golf ball will not move unless I whack it with the club. But what Newton also wants us to know is that once I send the ball flying, it will keep on traveling forever unless some other force stops it. That force is gravity, pulling the ball to the ground, or in this case, the water. The thing to remember is that the ball doesn't just run out of steam and fall to the ground. The force of gravity is stronger than the force I hit the ball with. An imbalance of forces, so gravity wins. You could apply the same idea to baseball. You hit the ball flies, but then it falls, pulled by gravity, and the fielder can catch it. Without gravity, well, now Newton was a pretty smart guy. He realized that this tendency of an object to just keep doing what it's doing at that very moment, to resist motion, was a natural property of everything in the universe. He called it inertia, the property of matter which causes an object to resist any change of its motion in direction or speed. Everything has inertia. How much inertia depends on the mass of the object, the amount of matter it contains. The more mass, the more inertia or resistance to being moved. Try taking a swing at a bowling ball instead of a golf ball. The bowling ball has much more mass, therefore much more inertia than the golf ball. Now that's a lot of inertia. Newton's second law of motion deals with acceleration. Now you may think that acceleration means to speed up or go faster, and it does. But in scientific terms, acceleration is any change in an object's direction or rate of motion. So in this instance, slowing down is a form of acceleration. Bouncing off a tree is acceleration. Even stopping is acceleration. And of course we know from the first law that the only way an object can do these things is if it's acted on by an outside force, right? So does acceleration depend only on force? Well, Newton figured out that an object's acceleration actually depends on the force acting on it and the mass of the object. Newton even made it into a formula. Force equals mass times acceleration. Really, it's just a fancy way to say that the change in motion of this golf ball is determined by me hitting it with the club and by the mass of the ball itself. That's why the golf ball will fly quite a ways, while the bowling ball only moves a few inches, even though I hit each with the same force. Oh, and one more thing. The force and the acceleration are always in the same direction, which is why the ball always goes in the direction I hit it. Well, almost always. The third law of motion is one I bet you've heard before. It says that for every action there is an equal and opposite reaction. Pretty simple. A great way to demonstrate it is with this little toy I found. It's called a Newton's cradle. The force of one steel ball hitting the rest of the balls causes one ball to react at the other end, an equal and opposite reaction. Any guesses about what will happen when I drop two balls? Well, just as Newton's third law says, the force of two balls at one end causes two balls to react at the other end. No wonder why they named this gadget after him. The concept of equal and opposite forces is the whole idea behind rockets being able to lift off and defy the force of gravity. The thrust of the burning fuel pushes down, and the huge rocket pushes upward in the opposite direction. So, Now I had 3 laws from our good friend Newton to ponder. The first law of motion: an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside force. The second law of motion: acceleration. Any change in the motion of an object depends on 2 factors: the total outside forces acting on it and the mass of the object. And the third law of motion: for every action there is an equal and opposite reaction. I am preparing to go on a scuba expedition. One of the keys to safety in underwater diving is knowledge of another aspect of forces: pressure. The science of pressure is behind so many things in our lives, and it relates to a very simple idea: pressure equals force over area. Think of it this way: lay a brick sideways on a surface. The force of the brick, its weight, on the area below determines the pressure. If you stand the brick upright, the same force is now on a much smaller area, so the pressure is greater. A knife is a good example of how pressure is used too. When you apply force to a very small area, the resulting pressure allows you to cut. That's what we mean when we say something is sharp. All the force is concentrated just on the thin blade of the knife. Divers have to deal with water pressure. That's the force of the water around them pressing on the surface area of their bodies. Think of it this way. We all know that water has weight, right? Well, the deeper a diver goes underwater, the more water there is pressing on him. And the pressure can get pretty intense. Even though the body is able to adjust to this increased pressure, it still poses a danger to divers. If they come to the surface too quickly, the change in pressure can actually cause bubbles to form in their blood. This condition is called the bends. And to avoid it, divers come back up nice and slow. So we know that the force of water pressing in creates water pressure. Well, it's no different with air. In fact, it's the same idea, because believe it or not, air has weight. And the force of that weight pushing on anything is called air pressure. Changes in air pressure can create some pretty amazing forces. Let's visit our lab world to investigate how.
Let's find the answer.
Here are a couple of fun experiments you can try that clearly demonstrate how increasing or decreasing air pressure can be a force to reckon with. You'll need the following materials: a glass milk bottle, the old-fashioned kind, a hard-boiled egg, a can of soda, a shallow pan of ice water, a Bunsen burner or candle, tongs, some paper, and matches. Yep, we're going to be lighting a flame here, so you'll also need an adult to help out. First, hard-boil an egg. After it cools, carefully peel the shell off. I like to make more than one egg so that I don't have to eat the experiment. Here comes the fun part. Have your handy adult supervisor light a piece of paper and drop it into the bottle. Now quickly place the egg back on the neck of the bottle and watch closely. What do you think happened? Well, the flame used up some of the air in the bottle, creating a situation where there was less air pressure inside the bottle than outside it. The greater outside pressure simply forced the egg down into the bottle. Now you know why I always have more than one egg, and how an imbalance in the force of air pressure can move things. Here's another way to see the force of air pressure at work. Take your empty soda can and fill it about 1 to 2 centimeters with water. Now, with your ice water close by, heat the can over the flame using the tongs for about 2 minutes. Now quickly and carefully turn the can over and submerge it about halfway into the ice water. Do you know why the sides of the can are pushed in? Must be a difference in pressure, right? You got it. When we heated the can, the air inside warmed up and expanded. The heat also caused some of the water to turn to steam. It was pushing against the insides of the can, but it didn't explode because the pressure could escape out the hole in the top. But when we put the can in the ice water, the steam recondensed and the air inside cooled very quickly. The air pressure outside the can was now higher than the inside, and since we turned the can upside down, the hole was now covered. The only way for the forces to balance was to crush the can. In both cases, the egg and the soda can, we were able to see clearly that when forces, in this case air pressure, are out of balance, you get movement. Before I finished with forces, I wanted to show how understanding the physics of forces can be important in our everyday lives. We've seen how forces are all around us, all the time, and how they are responsible for all changes in motion. But does that help us explain why an egg breaks when you drop it on the ground? Well, let's see. As the egg falls, it is obviously in motion. But when it hits the hard ground, the motion changes very suddenly. So suddenly, in fact, that the force on the egg increases to the point where the egg is crushed. But if you drop an egg on something soft, say a cushion of marshmallows, the change in motion is much slower. The egg sinks into the marshmallows a bit, slowing it down so it stops without breaking. This is the same idea behind airbags in cars. A slow change in motion results in a much safer stop. Day 229, Science Quest Wrap-Up. I learned quite a bit about forces today. First of all, forces are always a push or a pull on an object, causing a change in its motion, and they are involved in every part of our lives. In fact, the shape and motion of our world and everything in it is due to the balance or imbalance of all kinds of forces. Friction is a force that opposes motion. The force of gravity pulls everything down toward Earth, and even within the tiny atom, nuclear forces are at work shaping our world. I discovered that a pretty cool scientist from long ago, named Isaac Newton, came up with 3 laws about motion that give a good understanding of how forces affect us. The first law of motion: an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside force. The second law of motion: acceleration. Any change in the motion of an object depends on 2 factors: the total outside forces acting upon it and the mass of the object. The third law of motion: for every action there is an equal and opposite reaction. Then I took a dip in the ocean to find out that force over a given area is what creates pressure. Water pressure in this case. And the same idea is what causes air pressure. I even did some fun experiments that showed how an imbalance of pressure can make some pretty strange things happen, like sucking an egg into a bottle and crushing a soda can. All in all, not a bad day, I'd say. Well, so long for now, your fellow traveler.